A very good morning to Sir. In our Group 2 Session 3, we will present the computerized gear system. And here's our team member. The first is Jirowasan, and second is Chayasin, and third is me, Fujunwei, and the fourth is Chamuli, and the last is Hafik.
Hello everyone, my name is Kirivasan Muthu and my matrix number is CD240351. Today I'm going to present about the theory of our project, our presentation for the lab, which is computerized gear system. So basically what a gear system does. A gear system does is a gear system transfers power and motion between rotating shafts using machine feet. It allows us to change speed, torque and direction of the rotation. So basically, the gear ratio compares the input speed to the output speed. So basically, the formula is GR equals to N2 over N1. So it can also be written using GR is driven speed over driver speed. A high gear ratio produces high torque but low speed. A low gear ratio basically produces high speed but low torque. And next, let's go. I'm going to talk about the efficiency, which is N. Efficiency tells us how much useful power is transmitted. The formula is N is power P out over P in. So basically, that's the formula. Efficiency drops because of friction, backlash, misalignment, and lubrication issues. So, in compound, gear trains more than one gear stage is used. The total gear ratio is the product of each stage. This allows large speed reduction in compact design, similar to gearboxes and robotics. So next, torque speed relationship. Gear follows the power relationship P equals to T. Okay. So when speed decreases, torque increases. This is why vehicles use low gear for climbing, high torque and low speed, and high gear for cruising. So another thing is when we compare theoretical and experimental values, they are not same because the real system has friction, heat, fluid wear, and alignment issues. These losses reduce the output speed and efficiency. So that's the my part. That's for my part. So thank you.
Hi, my name is Chanmanli and my matrix number is CD240300. I'm going to explain about the observation. The experiment with the computerized gear system provides several key observations regarding the function and performance of compound gear trains. Most notably, the fundamental operation of the system clearly demonstrates the primary purpose of a compound gear train, achieving a significant reduction in rotational speed from the input motor, gear 0, to the final output shaft, which is gear 3. This visible reduction in the rate of rotation is necessary for the system to transmit power and motion. Consequently, the visible decrease in angular speed must be accompanied by a corresponding increase in output torque. Compare the input torque illustrating the fundamental torque speed trade-off of a gearbox. For example, when the motor is set to a low speed, the output shaft is observed to rotate very slowly, which suggests it is delivering high torque. A comparative observation between two gears set, the four-stage gear with same size gears, set 1, and the four-stage gear with different size gear, which is set 2, shows the two systems are engineered to produce different level of speed reduction. The physical arrangement of set 1 with its high number of driven teeth, which is 78, relative to the driven teeth 18, repeated across stages, is visibly designed to yield a much higher overall speed reduction and thus a higher gear ratio than the more graduated uh, steps in set 2. Furthermore, throughout the operation of both gear sets, it is observed that the speed values expected from the gear teeth ratio. This discrepancy is an important observation indicating that real-world factors like friction between the machine teeth, misalignment, and bearing losses cause power to be lost, meaning the actual output speed is slightly lower than the ideal theoretical output, thus defining the system efficiency. Thank you.
In the experiment, there are two tests are conducted. One of the tests is four-stage gear with same size gear, and from the table, The number of T and the pitch diameter is given, so we can calculate the gear ratio from the data given. Then we get 4.333 for three data because of the same size gear. And the total gear ratio will be 4 times 4.333 times 4.333 times 4.333. Then we will get 81.352 for the total gear ratio. So after the theoretical calculation, we need to calculate the total gear ratio for each motor speed from 100 RPM to 700 RPM. So how to calculate? Just use the first gear, which is motor speed, divided by the gear 3. Then you get the total gear ratio for each speed. So let's calculate the average total gear ratio for all speed. First, we have to calculate the total gear ratio for each motor speed. Let's see the 100 RPM first. So calculate the gear 0 over gear 1, then gear 1 over gear 2, and gear 2 over gear 3. Then times the three value together, then we will get 83.333. Do the same step until 700 RPM, then we will get the average total gear ratio. So given that the power output is 20 kilowatt and efficiency is 0.7, then we will get the power output since efficiency equals to power output over power input. After that, we can calculate the angular velocity, which use the formula 2 pi n over 60. Then where the n equals to the speed, after getting the angular velocity for the three gear, then we just substitute into formula to get the torque. And last, we calculate the efficiency again. We need to calculate three times, which are gear 1 to gear 0, gear 0 to gear 2 to gear 0, and also gear 3 to gear 0. Then we continue to the calculation for four-stage gear with different size gear. So just use the same steps as before to calculate since the pitch diameter and also the number of T are given. First, we calculate the gear ratio and the total gear ratio. Of course, the gear ratio will not be the same because of different size. Then we times 3 of the gear ratio together to get the total gear ratio. Then we calculate the total gear ratio for each motor speed, same as before. After getting each total gear ratio for different motor speed, then we calculate the average total gear ratio for 7 speed, which is 100 RPM until 700 RPM. Then we calculate the output power by using efficiency and the input power also. We calculate again the angular velocity, which from gear 1 to gear 0, gear 2 to gear 0, and gear 3 to gear 0. Calculate again the torque by using the angular velocity just now. And lastly, calculate the efficiency also.
Next, we will continue with the discussion. First, we compare the gear ratio theoretically and experimentally. According to the table result, it showed that the total gear ratio of the same size is higher than the different size. For the same size gear, the theoretical ratio was calculated as 81.352 and the experimental is 81.152. This difference only very small error. This indicated that the experimental result is closely matched to the theoretical prediction. This showed that due to the frictions, black ash of or misalignment are minimal and the system operates with the high efficiency. In contrast, for the gear of the different size, the theoretical ratio was 59.967, whereas the experimental ratio was significantly lower at 52.907. This large deviation highlights the influence of critical factors such as increased sliding frictions, black ash, shaft misalignment, or elastic deformation, which are more pronounced when gears of different sides of engage. Next, we will discuss about the input torque and the output torque of the gear system. Given that the input power is equal to the 20 kilowatt and the efficiency N is equal to the 0.7, and first we calculate for the input torque for gear set 1 and gear set 2. and you can get the same answer. There is 1909.86 nm, and we using the efficiency formula to calculate the power output, and we get the 40 kilowatt. And finally, we calculate the output docket for gear 7, and we can get the 111,408.46 nm. And for the gear set 2, we can get 60,768.2 nm. To calculate the efficiency of the gear system, for the gear 7 and 2 of the following combination gear, and given the input power is 20 kilowatt and the system is ideal, and first we calculate for the gear set 1. The gear 1 to gear 0, we can get the gear 0, the angular velocity is 10.47 radius per second, and the gear 1, the angular velocity is 2.377 radius per second, and the input torque we calculate and get 1910.2 nm, and the output torque is 5889.8 nm, and finally we get the efficiency is 0.7. And for the gear 2 to gear 0, we can get the gear 0 is 10.47 radius per second, and the gear 2 is the angular velocity is 0.7121 radius per second. And next, the input torque rate we can get is 1910.2 nm, and the output torque rate is 19,660 nm. And finally, we can also get the same result as the 0.7 efficiency. And for the gear 3 to gear 0, the gear 3 angular velocity is 0.1257 radius per second, and the input torque you can get 1910 and 0.2 nm, and the output torque is 111,000 the 376 nm, and we also have the same efficiency is 0.7. And next, for the gear set 2, the given to gear 0, the gear 0 is 10.47 radius per second, and the given the angular velocity is 4.97 radius per second, and the input torque is also the same 1910.2 nm, and output torque is 2816.9 nm, and the last efficiency is also the same 0.7. For the gear 2 to gear 0 and the gear 3 to gear 0, we also do the same step and we get the same efficiency 0.7. The last discussion we make is beside then compound gearing, given another type of the gearbox construction and also describe the applications. So the answer is an epicycling geartrain or planetary geartrain includes three main parts. There is a central sine gear, planar gear that rotate around it, and an altering gears. The plane gear mesh with both of the sun's gear and the ring gear by fixing one part and moving another. Different speed ratio can be achieved in a small space. These gear trains are commonly used in automatic car transmission, allowing smooth gear change and various speed options without needing a large gear system. They are also found in industrial machines like conveyors and mixer high where high torque is needed in tight space. In aerospace, they are used in helicopter and airplane engineers for efficiency power transfer while keeping weight low. The advantage of the epic cycling. Gear trains improve their complex size, flexibility, and efficiency that handle heavier load with less wear because the torque is shared among several plant gears. This makes them a great choice for applications where space and durability are important.
Assalamualaikum warahmatullahi wabarakatuh. Lastly, for the conclusion, the experiment showed the gear ratio, torque, and efficiency depend strongly on gear size and alignment. Gear 1 produced a higher reduction in torque than Gear 2, and the experimental values were close to theoretical one, with small losses due to friction and misalignment. Overall, the result confirmed that compound gear trains effectively increase torque while reducing speed, and their performance is influenced by gear design and mechanical losses. That's all from us. Thank you.